welcome to our 2022 somewhat summer student project seminar. We've been doing these for the past couple of years between Brookhaven and Argonne, and glad to expand out and bring Lexi and Christian from PNNL on, and hopefully we can keep expanding this more and more as we go. So we're going to limit this each presentation to about 15 minutes. I'll put my hand up, in the team's reaction here when you get to 10 minutes, and then we'll pop in and chime in when there's a minute left. So we do want to try and keep on the time schedule here. So so if we can get started. We'll start with Christian here, talking about mid-size UAS ABL measurements over the Southern Great Plains.
All right, thanks, Adam. All right, everyone. So like Adam said, my name is Christian. I am a DOE SUI intern at Pacific Northwest National Laboratory this summer. I'm a rising senior at the University of Oklahoma in the meteorology program. And my mentor this summer has been Lexi Goldberger. My work is titled Midsize UAS ABL Measurements over the Southern Great Plains. So I worked with a lot of raw data from a campaign that took place from November 4th through 16th, 2021. It was a collaboration between PNNL's ARM Aerial Facility and the Mississippi State University Raspet Flight Research Laboratory. So the aircraft took off from Blackwell-Tonkawa Municipal Airport, right off I-35, hereabouts, and then it flew 13 miles to the southwest to conduct its flights over ARM's SGP facility near Lamont, which is about 110 miles north of where I am here in Norman. So the aircraft used was a Raspet Flight Research Laboratory owned Navmar Applied Sciences Corporation Tiger Shark. It was outfitted with a host of probes and optical sensors, and of particular interest to my work is the Avantech Ames 30 probe, pictured here under the wing of ARM's Arctic Shark. And someone is unmuted. If you could check and please mute yourself. So yeah, among a few other variables, the probe measures pressure, temperature, wind speed and direction, relative humidity, and from those, it's quite simple to derive dew point. So the Tiger Shark flies a variety of flight patterns shown in this figure here. In quadrant A is the spiral flight pattern, which is often used for observing the vertical properties of the atmosphere, such as layers of temperature inversions and things like that. Then in quadrant B is the ladder pattern. Quadrant C is the parking garage pattern, and both of those are useful for obtaining vertical profiles, and in particular, more in-depth aerosol and turbulence measurements and vertical profiles of aerosol and turbulence measurements, because their legs of straight and level flight provide multiple data points for a single altitude, and they also provide the most efficient sampling of aerosols from the aerosol probes. And then in quadrant D here is the lawn mowing pattern, which is often used for obtaining surface imagery and information about other surface variables. Here are two actual flight paths flown from the campaign that I plotted, and we're going to be looking at some thermodynamic profiles from these two flights. So on the left is a ladder pattern from the 9th, and on the right is a compact parking garage pattern within a more normal looking, larger parking garage pattern. And both of the boxed areas are directly over ARM's Southern Great Plains facility. So to initially gauge the value of the data we're getting, I just plotted this simple thermodynamic profile from the ladder pattern flight on the 9th. And so we can just ask ourselves, what does this tell us? We can immediately see that there are steep lapse rates just off the surface. That is temperatures decreasing rapidly with height. And then above that, there are actually a couple strong temperature inversions. And this is often characteristic of a post-frontal environment. I was able to confirm that a cold front had moved through here a few hours before the flight by looking at some surface observations from a nearby Oklahoma Mesonet station. So here's the same data compared to a few things just to kind of get a measure of its accuracy and validity. So on the right, it's compared to 2 weather balloon launches, and on the left, it's compared to an interpolated sonde value-added product. So what that is an automated process that takes the data from these 2 balloon soundings, and then it just interpolates that to get an idea of what the atmospheric characteristics would have been like at any time between those balloon launches. And in this case, it's for the middle of the time that this profile was taken from the UAS. So in all of these plots, the y-axis is altitude, the light reddish pink line is temperature measured from the UAS, the blue line is dew point from the UAS, and for the wind variables, the blue line corresponds to the UAS data. So overall, I would say that the general trends and shapes of these profiles compare reasonably well to the sonde data. Obviously, the altitudes of specific features like that inversion there changed a little bit throughout the day. And then here's the same stuff for the 11th. And I would say that the profiles would actually line up a little better on the 11th. And that could be maybe evidence that the flight pattern flown on the 11th is better suited for taking these profiles. But I would say it's most likely and largely due to the fact that the atmosphere was just a lot more dynamic on the 9th because you'd had that cold front move through. So things were changing a bit more than on the 11th, which is what we would perhaps call a boring weather day, where it's easier to get these consistent measurements of the atmosphere. So a few things you may have noticed from both days. First thing is that the wind direction for the interpolated sonde is pretty far off from the UAS wind direction and also from the actual observed sonde data. So that's something on the interpolated sonde side of things and nothing to do with the UAS data. And then also, even after I've applied smoothing techniques to all the UAS data, still the UAS wind speed and wind direction too have a lot more fluctuation and sort of jumpiness than the sonde data does. But I don't think that this is bad data. In fact, it's kind of expected to be a little bit more erratic. And that just has to do with the sampling method of an aircraft will inherently have a little bit more fluctuation because, as I'm sure you know, an aircraft flies horizontally. So that allows it to obtain more data points within a given interval of altitude. And the more data points that there are within that interval, the greater chance there is for there to be some variation. And also, as an aircraft flies horizontally, it has the opportunity to fly through some different air currents, as shown in the schematic here of an aircraft flying through an idealized thermal. So you can see it would fly through some sinking air, and then some eddies and some rising air, then air going in the opposite direction to replace this air that's being lifted out of here. But a sonde, on the other hand, it's more of a Lagrangian reference frame, meaning that yes, it is rising, so it will potentially go through some different air currents with altitude, but any horizontal changes in the wind measurements would likely mainly be limited to as the flow itself that is carrying the balloon evolves. And I actually spent most of my time this summer working on sensible heat flux calculations and trying a few different methods based off of ones I've read from research papers. So I used a November 13th flight that flew the lawn mowing pattern, and I ended up settling on the Eddy covariance method with the formula shown here. And to find the covariance between the vertical component of the wind and temperature, I used spatial averages rather than temporal averages like the Python function would normally do. And that's because temporal averages have been shown to cause a low bias in sensible heat flux calculations. But here is a plot of the sensible heat flux The black line is, well, it's a time series, and the black line is sensible heat flux measured from a surface station at the SGP site. And all of the little colored segments are sensible heat flux as calculated from straight and level flight legs, and they're color coded by altitude. Now, what we would expect to see is that as altitude increases and you get to the top of the atmospheric boundary layer, that sensible heat flux would approach zero. And we would also probably expect to see an upward trend in sensible heat flux like the surface station shows as surface heating and solar radiation increase throughout the day. Now, we don't see either one of those relationships, and there's really no leg-to-leg agreement. You can see from one leg to the next leg, there's some substantial jumps. So why the inconsistency? Well, it goes back to the erratic wind data, particularly the vertical component of the wind that goes into this calculation. And that vertical component of the wind is plotted here in this figure, and it's only taken during straight and level flight, so we wouldn't expect anything too crazy to go on. Well, it's not only taken during straight and level flight, but I applied a data mask to only look at straight and level flight. Yet we still see these almost cyclic looking jumps and fluctuations in this vertical component of the wind. And I wouldn't expect to see that naturally occur in the atmosphere, so I can fairly confidently say that this data set is in need of revisiting. We believe it to be a data processing issue, so we've submitted a data quality report because, again, we don't believe that it was a data collection issue or a probe malfunction or anything like that. But hopefully this data can just be reprocessed and then corrected and used for some future research. So to conclude, mid-size UAS have been shown by this campaign to be well suited for surveying the boundary layer due to their specialized flight paths that fit the needs of the mission depending on the variables and data that researchers are interested in. And I showed that data gathered compares well with sonde data, and it can supply valuable information such as how I could tell that a cold front had moved through a little bit before that flight on the morning of November 9th. And the heat flux and energy budget research does show promise, but a little more work is needed just to maybe improve upon and ensure the validity of this method given good wind data. And since I made this presentation, I have applied that method to several other, or to data from several other campaigns. And it wasn't nearly as there was a lot more agreement from leg to leg. However, the first campaign that I applied it to, the aircraft flew well above the top of the ABL, so pretty much all of the values were zero or around zero as expected. However, just today I applied it to another campaign, and the aircraft flew quite low, but still most of the values were at around zero. So not exactly sure what's going on with that. I'll have to look into it a little bit more. So I would like to thank my mentor, Lexi Goldberger, and acknowledge that this work was supported in part by the DOE Office of Science, WDTS, under the SUI program. Thank you. I'll open it up to questions now.
Great, thank you. That's great you were able to work with data close to home. So are there any questions out there? If so, please raise your hand, and maybe while they're thinking, I'll ask, so what sort of QC and kind of data cleanup did you have to do to get some of those nice smooth plots from some of these profiles?
Good question. So what I did was I separated all of the data taken from straight and level flight. Well, first I applied a straight and level flight data mask just based on changes in altitude and changes in heading. So if the data was taken during a leg of straight and level flight, then I separated all that data into 20-meter intervals, and then I averaged those 20-meter intervals to get one value for each for every 20 meters. And then I just linearly interpolated those values to get it back down to 1 meter intervals.
Okay, great. Scott, I see your hand up, and we got about a minute.
Very quick question then. Really great talk. I really enjoyed it. What were some of the challenges you faced during your internship in using some of the data or learning some of the arm science?
Good question. I'd say one of the biggest challenges was at first I kind of dove into it without doing much of a literature review beforehand. And as I mentioned, for the Eddy covariance method, from a moving platform, you should be using spatial averages rather than temporal averages. But I didn't know that without reading some papers beforehand. So I was using the temporal method and ended up having to kind of start over.
Very cool. Thank you.
All right. Thank you very much. If there's any questions, any more questions, please do follow up in the chat. With that, I think we can move on to Maggie here to talk about objective analysis of storm morphology in radar data. So Maggie, please.
I'm on mute. All right, can everyone see my presentation?
Yep.
Awesome. Yeah. All right, so hi everyone, my name is Maggie Zerner. I'm a Sully intern at Argonne National Laboratory this summer, working with Robert Jackson and Bhupendra Rao. I'm also an undergraduate meteorology student at Iowa State University, and I'll be discussing an objective analysis of storm morphology and radar data. So a little background into my topic. Why do we want to study storm shape or its morphology? Storm shape can provide us key information about a storm's dynamics that influence its development, evolution, and its behavior, and tell us a little bit about the different atmospheric ingredients that are going into storm development, as well as the potential influence that storm will have on its surrounding environment. So we'll take a look at two different examples of two different types of storm shapes. On the left here, we have an example of a bow echo, and this is characterized by its bowing shape. And bow echoes are commonly associated with large amounts of precipitation, strong straight line winds, and occasionally some tornadoes produced within embedded rotation in the line of storms. And if we look at the storm here on the right, this is a supercell, and we can see the hook echo starting to form, telling us that there's a lot of rotation going on within the storm, and supercells are the most likely type of thunderstorm to produce tornadoes. So just based off storm shape alone, we can already tell a lot about these two different types of storms. So current numerical prediction models have some difficulties with representing the storm morphology, and this can lead to uncertainty in forecasts, as well as a need for improvement within these models. And current analysis of morphology includes either a manual classification based on appearance, similar to what I just did with the one of the last few slides, where I looked at two different radar images and I said this is a bow echo or this is a supercell just based on the storm shape. Or analysis can be done by a classification just based on a single parameter, which, for example, could be the ratio of the major to minor axis, which wouldn't really separate bow echoes from more linear types of storms, as that's only looking at the aspect ratio and not any other parameters. So, as you can imagine, these techniques don't adequately represent a storm's shape or the shape's dynamics or characteristics as a whole. So our motivation behind why we wanted to start this project is we wanted to answer the question, is the automated analysis of storm morphology a feasible technique? And in order to do that, we want to apply machine learning to improve the accuracy at which this morphology is predicted for these storms. And that's because morphological parameters can quantify the shape characteristics of the types of images that we're looking at, which makes it possible to classify these shapes. Onto the methods that we used throughout this process, we gathered data from the Amazon Web Services, which was completely free and available to anyone who wants to expand upon this in future work. And we used the NexRad radar reflectivity. And we gathered this data for an entire season for summer of 2020 at the KILX radar site, which is in central Illinois. And following that, we used PyArt to map this data onto a Cartesian grid, and an example of what that data that we're working with is shown on the right here with the reflectivity. Next, we used some image processing techniques to remove noise. So we removed all reflectivities that are lower than 35 dBz, as that's typically a number used to separate convective precipitation from stratiform rain. So we eliminated all the reflectivities that are lower than 35 dBz. And then we used OpenCV's library to perform contour analysis and found some shape parameters, which I'll go into here next. So this is what contour analysis typically looks like using OpenCV. On the left here, we have our original image, and this is a radar image with the reflectivities lower than 35 dBz being removed. And then on the right, highlighted in the green, are the external contours found using OpenCV. And in this project, since we removed smaller radar echoes and only focused on the largest echo within the shape, then this more central, I don't know if I can annotate here. Yeah. I can. So this more central echo would have been the echo that is analyzed in this example. Next, we found the image moments, and these are important and a commonly used technique in image processing to provide information about an image's intensity at a certain pixel, and these are unique to each image. And we also, from the central moments, we found the moment invariants, and those are invariant to scale, translation, and rotation, which means that this technique can not only be applied to just radar images, but it can also be expanded to other atmospheric data, which includes satellite images. And then we calculated a few parameters in OpenCV, and I'll give a physical meaning behind a few of them. This is compactness. So on the left here, we have a low compactness shape, and that's because its shape is more widespread, taking up more surface area, versus on the right here, much of its mass is concentrated towards the center. So this object would be more compact. Next was roundness, and the shape on the left here has more sides and is more similar to a circle. So this would be more round, whereas on the left, we only have 4 sides and it's less similar to a circle, so it's less round. We also used elongation, and this is the measurement of the length to the width by the bounding box, which is indicated by this rectangle around each shape. So this shape here on the left would be more elongated versus this shape in the middle here would be less elongated. We also found eccentricity, which is similar to elongation, except this is using the object's perimeter rather than a bounding box that surrounds it. So here we have a high eccentricity shape. Again, it's more long than it is wide, and here's a low eccentricity shape. It's more circular. We also use skewness, so I drew the x and y axes on here. A object that is more positively skewed in the x direction would have much of its mass on this side. If a object was more positively skewed in the y direction, it would have more mass on this side. So this is just to quantify which direction that this object is skewed in. Next, we performed a statistical analysis by using a correlation matrix, and this would help us determine the degree of correlation between these different parameters. And this would help us identify which parameters would provide the most important information about shape, and we'll get into some of those relationships in a few minutes. Next, we applied some machine learning techniques and clustered these radar images together based on similar shape characteristics. And we did this to ultimately determine whether or not it would be possible to identify and categorize shapes automatically. And on to some results. So here's a correlation matrix that we found. I'll just note a few things here. The darker blue colors indicate a more positive correlation, and the darker red colors indicate a more negative correlation. So some things that stick out here are that compactness and roundness are inversely related to each other pretty strongly, but they're not a perfect relationship, which tells us that although some shapes may be compact and round, it doesn't explain that for all shapes that are compact, they're not always going to be round. Some of them are also, roundness is also related closely to area and perimeter, as well as equivalent diameter. There are some other relationships here to note that skewness and in the x and y direction are related to deviation from circle, which makes sense because as a shape is more skewed to one side or another, it becomes less similar to a circle. So those are just some few things to note, but what is most important here is the parameters that don't have any relation to other parameters at all, because those don't depend on other parameters. If a parameter is related to another, then they are basically telling us the same information about each other. So we want parameters that aren't closely related to any of the other parameters. Next, we did the principal component analysis, which helps us to reduce the dimensionality of the data set because we did have 12 parameters that we were working with. Reducing it down to 2 helps us to visualize the data set a little bit easier. And then we used the elbow method to determine the number of clusters that we should use. We were aiming for a number between 3 and 5, and we ended up with 4. And then within each cluster, we found that each one contains its own set of radar images with distinct and unique shapes. So we'll look at an example that came out of each cluster. This is the type of storm that came from cluster 1, and it's this more linear shape with its y component much larger than its x component. So these more linear storms versus in cluster 2, we had these more horizontal storms. So it's almost the opposite case from cluster 1, where much of the mass was spread across the y-axis, and these are more x-axis distributed storms. Looking at cluster 3, these didn't tend to follow any specific axis, and they were just more widespread, taking up more surface area and not following into a certain linear shape. And finally, with cluster 4, they were more isolated, discrete cells of precipitation, rather than large lines or more widespread convective systems. These were more isolated areas of precipitation. Now onto the discussion and the future applications. So these results indicate that this technique is feasible because we wanted to determine whether or not we would be able to group these storms together based on their similar shape characteristics. And from each of the different clusters, we saw that each one contained its own set of distinct shape characteristics. Cluster 1 had these more linear shapes, cluster 2 had more horizontal shapes, cluster 3 was more widespread, and cluster 4 was more discrete cells. However, this technique does need refinement as noise, broken convection, and other cases that need additional consideration could skew the results. If we look at this image on the left here, there are some areas that the convection is broken, so that would need further consideration to be accurately represented by this algorithm. In the future, we hope to provide a database of classifications of convective systems to the US DOE Atmospheric Radiation Measurement, or ARM, user facility to improve atmospheric research. And we also hope to develop a Python package that can perform automated morphological analysis of convective systems as an open source software for advanced research. And to wrap up, we wanted to answer the question, is the automated analysis of storm morphology a feasible technique? And though this process does need refinement and special cases do need more consideration, our answer is yes. We were able to classify these different types of storm shapes into different categories based on their similar characteristics. And the impact of this is that this method can be used to improve the accuracy of weather and climate models and advance atmospheric research. And thank you. Does anyone have any questions?
Okay, great job there, Maggie. Do we have questions? It looks like Maria.
Yes, Maria.
Hi, Maggie. Great job.
Thank you.
Good. My question is about the second type of storm you showed in the cluster. I think your example had a storm that was cut off by the image. So the full storm wasn't in the image. And
in cluster 3.
Oh, cluster
Yes.
3.
Yes.
Yeah. And I was wondering if that is also a problem because we don't know if this maybe was has a different shape of the image.
Definitely. And there were a lot of cases like that where the radar image was cropping out some of the storm. So that's definitely another consideration that we need to take into or keep in mind, that we're not getting the full picture of the full shape.
Thanks.
Great. Shaima.
Yeah, no, this was really great to see. I guess my question is, thinking about extending this to other types of data sets, what do you think some of the challenges might be if you wanted to, say, apply this to visible or infrared satellite data?
Yeah, I think it could be, the scale. Some of the parameters that we calculated aren't scale invariant, while some are. So adapting this kind of method to the scale that we're looking at would definitely be a challenge.
Okay, any other questions? We still got a minute or two here. I guess I'll ask one. So it sounds like you thresholded these based off the reflectivity, and you can still see some speckle in these images. Were you looking at using maybe other polarimetric variables from the radar to further threshold these data?
Yeah, so the only thresholding we did with the radar images was removing that reflectivity that was lower than 35 dBz, but then we did remove the smaller echoes that contain less than 175 pixels, so that it would only focus on the largest clustering of pixels in the image. So that was the further thresholding that we did, but we didn't do any more thresholding with the radar data itself. That's a good question.
All right. Well, if there aren't any other questions, thank you, Maggie. We will move on to Daniel with classification of atmospheric LiDAR data for edge computing.
Okay, can you see my screen?
Yes.
Okay, that's good. All right. My name is Daniel Zetterberg. I'm a rising senior at the University of Tennessee studying physics, and this summer I'm working at Argonne National Lab through the SULI program. I'm working in the Environmental Science Division with Bobby Jackson, who is an atmospheric scientist here at Argonne. The focus of my project is using machine learning to classify and cluster LiDAR data. The data comes from LiDAR sensors, which are shown in the bottom image right here. And the LiDAR sensors are associated with waggle nodes, shown right here in the upper image. The waggle nodes contain edge computing capabilities, which is when data is processed directly on a sensor instead of all of the data from the sensors being sent to a central computer to be processed. And the LiDAR sensor shown here is at Houston. Thanks, Bobby, for taking a picture of it for me. But the LiDAR sensor that I'm working with is located at the DOE ARM facility at a Southern Great Plains site in Lamont, Oklahoma. And the effect of cloud processes and feedbacks on climate is a major uncertainty in current climate models. In current models, clouds are modeled using empirical data collected in part from LiDAR. By collecting more cloud microphysical data such as drop, shape, count, and size, climate models can be improved. The LiDAR at SGP will be used to collect LiDAR Doppler spectra of particles in the atmosphere. However, as of now, only 2 months of LiDAR data have been recorded at the SGP site, and 1 hour of LiDAR data is about 500 megabytes large, so it's not practical to store and analyze all of it. Where my project comes in is to develop a method that automatically classifies the data. So Doppler spectra from cloudy days that has the data that we want is stored, and Doppler spectra from clear days is discarded. I use the 2 months of LiDAR data that we have to create an algorithm that can classify the data in real time. This algorithm will be implemented into the waggle node. To classify the data, I use k-means clustering, which is an unsupervised machine learning method. The number of clusters is decided by the user, and you find the optimal number of clusters using the elbow method shown here. The distortion shown on the y-axis is the total distance from each point to its cluster center, and on the x-axis is the number of clusters. And the more clusters there are, the more time the algorithm takes, and the more difficult it is to interpret the physical meaning of clusters. Therefore, the number of clusters that minimizes distortion and runtime is chosen. In this case, the optimal number of clusters is 5. Each data point that I'm looking at has 5 dimensions, with each dimension being a data variable from the Doppler spectra of the LiDAR. The Doppler spectra shows the distribution of Doppler velocities and the power of the LiDAR reflected off of the particles. The 5 dimensions/variables are kurtosis, which is a measure of how flat or how sharp the curve is, Skewness, which is a measure of if the curve is skewed positively, negatively, or neither. Spectral width, which is a measure of the width of the curve's peak. Signal to noise ratio, which is the ratio of the curve's peak to the background noise that the LiDAR records. And any data point with a low signal to noise ratio was thrown out. And Doppler velocity, which is the velocity that the curve peaks at. Negative Doppler velocity shows a particle moving downwards, and positive Doppler velocity shows a particle moving upward. Or particles, because the LiDAR, it covers like many particles, not just one particle. And we found that there are two groups of variables that have strong linear correlations. The first group is signal to noise ratio, spectral width, and kurtosis. The second group is Doppler velocity and skewness. And given these variables strong linear correlation, we found that we could reduce the 5 dimensions to 2 dimensions while retaining 99% of the information using principal component analysis, or PCA. PCA improves runtime and makes visualizing the data easier, but is normally used for datasets with more than 100 variables. However, using PCA before k-means still improved the runtime of our clustering algorithm. And to make sure that PCA wasn't taking out too much data, too much invaluable information, k-means clustering was also done without PCA. And between the clusters with and without PCA, only 1.5% of the data points were grouped into different clusters. And here's all the data points plotted into principal component space. The plot on the right shows the data points plotted by cluster. And the red dot, the red X's are the cluster centers. And the plot on the left is a heat map that shows the density of the data points. Most of the data is concentrated near 0, 0 on the graph in the blue and gray clusters. 60% of the data points fell into the blue cluster, 29% fell into the gray cluster, about 5% fell into the green cluster, about 3.5% fell into the orange cluster, and 3% fell into the magenta cluster. And to define the physical meaning of the clusters, we looked at the average Doppler spectra of each point in each cluster and plotted the time periods where each cluster was maximized. And here's a plot of the average Doppler spectra for each cluster. The x-axis shows the velocities that the particles are distributed over, and the y-axis shows how much of the LiDAR signal was reflected from the particles. A negative skewness, such as in the magenta, shows particles moving downwards, and green, or like a positive skewness, shows particles that are moving upward. And from this, we were able to deduce the physical meaning of the clusters. And so, and these are plots of the LiDAR data points in the time range domain, with each point's color corresponding to its cluster. The plots show what the LiDAR sees looking up at the sky. And I made one. Each of the following 5 plots are the 1 hour time period where the frequency of each cluster was maximized. So here's the blue cluster, which is thin cloud and aerosol. The orange cluster, which is cloud and aerosol in the presence of weak updrafts. This is the green cluster, which is cloud and aerosol in the presence of strong updrafts. The gray cluster, which is stratiform cloud or aerosol. And the magenta cluster, which is rain or precipitation. To conclusions. The algorithm developed in this project will improve long-term observations of aerosol and cloud properties. The algorithm will allow the waggle node associated with the LiDAR data to separate cloudy days from clear days. Scientists will be able to analyze the data from cloudy days to gain more empirical data on clouds, such as drop size, number, and shape. And this data will be used to improve modeling of cloud radiation feedback and climate projections. Going forward, the most important work that is needed on this topic is the implementation of the clustering into the waggle nodes. And additionally, two discrepancies in the data must be studied. The first is that the outliers of the clusters will be investigated, specifically why they form distinct branches, such as in this photograph, like there's a distinct branch on the orange too, but there's nothing in between. So we need to figure out why that is. And also we need to figure out which data points do not match up between the clusters done with and without the PCA. And I'd like to thank Bobby Jackson, my mentor, for a lot of help on this, and also Bhupendra Raut and Max Grover for their help throughout the projects. Are there any questions?
Right, great work. Okay, any questions? So I guess Scott never lets
Really not. No, I think this work is so exciting. I love seeing the temporal coherence of those periods. Daniel, have you played around with actually getting this working at the edge, actually programming one of the waggle nodes, or is that more future work?
That's future work. I haven't started that at all.
Great, very exciting.
Right, Ernie.
So maybe a naive question, but could this be applied to other upward pointing sensors other than radar? If you're getting Doppler, could you, or other than LiDAR, I mean, could you use it for radars to some extent? Or some aspect of radars?
I don't see why not. I don't know exactly how a radar interacts with particles in the atmosphere, but I think it would work the same.
It's microwave instead of near infrared, so it's pretty. You could use a similar technique to try to tease out something like this too.
Yeah, thank you.
Mike.
Yeah, thanks. Very nice talk and interesting stuff. So at the end, you showed the six different clusters you had, and that I think you related them each to a different shape of the Doppler spectra, right? And I think use those quantities to try to say what physically that is. Have you thought about how to validate that?
We can. I have not been able to start this yet, but there's the weather conditions at the SGP site. The historic weather conditions are stored, I think, at an ARM website, and also images of the sky. So one thing to do would be to go through and look at the weather conditions at the 1 hour time frames for the clusters, and I guess that would be how you would validate that.
I would add also there's tipping bucket rain gauges and astrometers, so you can tell if it's raining. So whole suite of instruments at the SGP we could add onto this to verify that we actually are seeing cloud or rain. Because right now it doesn't. You wouldn't be able to say either way, which is why it's vague cloud aerosol mix. But I think the future work is to add some information from other ARM instruments and sensors to be able to distinguish between cloud, aerosol, and rain better.
And yes, it might also be interested too to look at the AAF flights of the UAS as well. At least, you know, if you're looking, can't go in the cloud, of course, but just in clear air, looking at the aerosol, the background noise that you're seeing here too. So that could be good in situ validation almost of some of these. Okay, any other questions? All right, well, if not, we'll move on to the next. Thank you again, Daniel. We got Matthew coming up next with Tracking Aerosols, Convective Interactions Experiment and Visualization. And we can see your slides here. You are on mute, I think.
Can y'all hear me now?
Yes.
Perfect. Oh, I'll go back. All right, my name is Matt. This summer, a second-year SULI intern. This summer, I got to work with Tracer as well as my kind of more individual project with Tracer visualization. And for the second summer in a row, I have Scott as my mentor. So a little bit about myself. I am a rising senior at the University of Oklahoma, studying meteorology. So me and Christian see each other quite a lot during the school year. And a couple things, just a little about myself. So I'm really glad I got to work on Tracer this year. I didn't get to work on it last year since it got postponed to this summer. But Tracer's really helped influence and improve my skills as a forecaster, programmer, and as a meteorologist. And as well as I gained a lot of research and real world experience. So Tracer stands for Tracking Aerosols Convection Interaction Experiment, and it's led by Mike Jensen, and it's based in Houston. So on the right, we have a map of just kind of some of the sites that we've been doing some stuff out of in Houston. And the reason why Houston was picked is that it's a great combination of both hot summer weather. Houston is the 4th biggest city in the U.S., so it does have a lot of traffic and aerosols from the urban environment, and as well as it's close to the Gulf, so it does have a sea breeze. It does kind of help with some of the convection that we'll be looking at. The motivation behind it is the broad overview of how convection works is still not 100% well known, and the influence of aerosols as well as the sea breeze on that, and trying to find those microphysical processes that are within convection storms to help improve the accuracy of weather models and predictions, and to find how what kind of influence does aerosols have on a convective atmosphere. There's some people saying it has a huge influence or it hampers it, and there's some people saying that it might not have as much influence as we think. So I'm part of the forecasting group for Tracer. So this group of forecasters mainly consists of meteorologists and stuff that we have a couple of main reasons to why we're part of the Tracer field campaign. And one of the main reasons is accuracy. The campaign relies on specific weather conditions and cloud types to conduct operations, and the campaign in general has very limited time and instruments. We have enough soundings, so upper air profile balloons, to do enhanced soundings or an enhanced operation day around every 4 days. So trying to have a forecast that could predict if a day's looking really, really good for operations or really bad for operations, that we use our equipment and the time wisely for the people who are in those operation groups, as well as analysis. This project will be probably looked at for years to come, and trying to look at how accurate we were at forecasting and what the models of for those forecast types and how accurate were they, as well as it kind of helps us analyze and look at days that are really good for looking at future case studies, as well as looking at some of the stuff that I've been doing on a more individual scale, and as well as it's a lot of good practice and fun, and it helps improve our communication, weather analysis, and forecasting skills. So what we're looking at here is our broad matrix forecast. This was done on July 27th, looking at the 28th, 29th, and then into that weekend. Everything I'll be showing is either a forecast for the 28th or what actually was visualized on the 28th, and that's kind of the one case I was looking at for right now. And we do forecast the lower, mid, and upper clouds coverage. And then we also try to forecast the convection to the best probability as we possibly can. And that we do that for all of this for the morning and afternoons for each day. And then we do a wind forecast for a specific location where some of the operations are being out of. So during this time frame, it was at Jones Forest in the Houston area, as well as we forecast a sea breeze coming in from the Gulf, as that really does help with the convective development of some of the storms that we've been looking at, as well as the aerosol part, looking at the ozone and the PM 2.5 forecast for those days. So looking at, excuse me, the more weather base of this forecast, of that forecast matrix. So we use a bunch of different models, charts, graphs to forecast this for Tracer, and some of the stuff that we've been using, just to select a few. On the top right, top left, we have our Weather Prediction Center short range forecast. It kind of shows a broad overview of the rain chances for the United States, as well as frontal motion and pressure systems. So some things to really pick out there is that There's a stationary front moving over Oklahoma, and as well as there's a hashed area of a chance of precipitation. And this was done at 12Z on Thursday. For anyone who doesn't completely understand what 12Z is, Z is just an abbreviation for our Coordinated Universal Time. So 12Z would be in Eastern, that would be -4, so it'll be 8 a.m. And then for Central Time, like us in Chicago, it would be 7 a.m. In the top right, we have our NAM model with our CAPE, and CAPE is convective available potential energy. So what is needed in the environment to form these convective storms, and this is over SIN, and SIN is convective inhibition. So basically what prevents storms from forming, usually a temperature inversion in the lower part of the atmosphere. And then the bottom left, I use this model, the Euro model, so the ECMWF medogram, to kind of help forecast cloud coverage as well as some precipitation chances and accumulation for that 28th of July. And then the bottom right, we have what we use for our sea breeze forecast. So we use the HERS temperature with wind isobars. And so a couple things to notice from this one is in the morning hours on the top 3 plots, there's not a huge temperature difference between the coast and the Gulf. And that when there's a significant gradient, usually is whenever we're able to identify maybe a possible sea breeze. So in the afternoon hours, we don't really see much, but when we get to 21Z, you start to see that line start to form along the coast. And then you see the wind start to blow those temperatures further into Texas, kind of indicating that there's a sea breeze going on. Some of the other things that we use is an ensemble paintball plot. So this kind of just shows the overarching view of all the models and what they're predicting. So for this day, this was at 18 UTC on Thursday, so around midday Thursday. And most of the models weren't showing much of anything. I think the only model to really show some stuff was the HER model, the 6-hour HER. So you can see in the top right as well as some of those isolated thunderstorms forming over the Houston area and the Bay Area as well. So the models weren't really showing much to go on this day, but we were in a kind of a trend of always having lower chances in the morning, but actually a decent chance in the afternoon with the sea breeze. So we also compare our forecast to the National Weather Service, and they were kind of in agreement that there was a more around a 30% chance for that Thursday afternoon to have some kind of convection. So when another part of the forecast is the air quality forecast. So we look at ozone and PM 2.5, and these are just some of the things that we kind of show to represent some of these values. So we use our GEOS ozone forecast, and both of them are for Conroe, so that's a more inland site in the Houston area. So on the top left, you can see on the very top part of the graph is our vertical profile for ozone levels, and then showing the broad values of ozone as it goes throughout the day. So we usually have that typical cycle of peaking in around the afternoon hours and then decreasing as we get through the evening and into the morning. And then the top right, we have our PM 2.5 forecast for Conroe as well. Nothing really going on significant through Thursday and Friday for that time slot. But then when we got into that weekend, we had a Saharan dust move in, and you could look on the Saharan dust forecast. There was a big plot of Saharan dust that started to move into that area on Saturday and going into Sunday. So to go a little bit more in depth on what I did on a more individual scale with Tracer, so I was trying to create a program to help visualize on a specific day and time what's happening in the Houston area. So I was pulling data from ARMS, ACARS, and other data sources that were used during Tracer, and to plot them on specific graphs like I showed earlier. But more of on instead of a forecasting side, more of an actual real-time side. So the uses of this is, to able to grab these plots very quickly and for specific times, and to compare them to other times in the day, or as well as the forecast, and to start to develop good case study days. So looking at that 28th visualization, so these are soundings from the morning of that day. I think both these were around 11:30 UTZ. So these are our upper air soundings. And some things, if for whoever doesn't know what these plots represent, the green lines going vertically showed the dew point, and then the red line shows the temperature of an air parcel as it moves throughout the atmosphere, and the black line is that parcel profile. So some key things to pick out here is on the ACAR sounding, when that red line in the very bottom is to the right of the black line, it kind of shows the SIN values, so that capping inversion, so a pocket of warm air that's preventing that would prevent thunderstorms from forming. And then on that on the left chart, we have that shaded red area that does show CAPE, so our convective available potential energy, and what's that there's still energy in the atmosphere, but there's still a bubble of air that's kind of preventing these storms from forming. And then here's later in the day when we started having some of the storms develop, and we had our reflectivity from our NextRad radar kind of show up in the Houston area just north of the bay, and actually moved pretty much right over one of the sites at LaPorte. And so our CSAPR vertical reflectivity radar showed that up pretty well. But a kind of interesting thing is that there's not much going on past around 4 or 5 kilometers above the radar. And when I was looking at kind of the enhanced soundings that we were conducted for that day, just around an hour beforehand, there was still a pocket of SIN in the lower parts of the atmosphere that seemed to be preventing them from forming. But once that, it seemed like that once that broke, these storms were able to form, and they just haven't been able to develop into deep convective isolated thunderstorms quite yet. And then lastly, our verification part of the forecast, I like to say this is like grading our work. So we verify each forecast a day of. So the 28th forecast, we verified it on the 28th. We go in green, yellow, and red boxes. Green means we were pretty much spot on the forecast. Yellow means we were off by a little bit. So example, this is the 20% isolated showers. That didn't really happen that morning, so we put that in a yellow box, but the probability of that was low anyways. And then a red box, we don't have any for that day, would be like if we said there was going to be any, like 0 sea breeze, and there was actually a significant sea breeze. We actually don't have a whole lot of red boxes throughout the summer so far, so that's actually been very good. And then some conclusions and for future stuff. So Tracer will continue through August and September. And the forecasting team will continue to maintain a vital role in helping the operation groups use their equipment and time wisely, as well as the forecasting team will help kind of find isolated days that are more prominent for operations, as well as kind of picking out some of those days that might be able to do some case studies with. And then the visualization program that I was able to make would help quickly help give access to anyone who wants to quickly grab some of that data from a specific day to kind of look at, so especially when it comes to case studies. And thank you guys for listening, and I believe we have time for questions. And
gotta go.
Can't see anything from.
Right, thank you very much. So do we have any questions? I would say I'm curious, did you use any of the ARM data when you're going through and doing your forecasting for somewhat real-time or near real-time looks at the data?
Yeah, so when it came to forecasting, we did look at a lot of those soundings around 11:30 UTZ. Those were usually really good indications for the what the environment was looking at in the morning. So I used those a lot, especially when doing the main forecast part of Tracer. And that was actually a really good indication for some of those case study days when we saw those pockets of temperature inversions.
Okay. Right, any other questions? I guess the last one I'll have, and then we can move on, is where is your code hosted? I'm definitely curious how you're working with the ACARS data and getting that into those SONs or into those.
I'm gonna post that probably later today or tomorrow onto my GitHub, and then I'm gonna work with Max Grover to try to get that into a cookbook to put on a I believe the PyArc website, or even something with Tracer. So that's something that will be probably done in the next 2 to 3 days before my internship ends.
Okay, perfect. That sounds good. Thank you again, Matt. We will move on to the next presentation, which is a joint presentation here. And please correct me, but Eamon, Emily, Noah, and Natalia.
So
Nice job. Nice job, guys.
All right.
Right, Noah, hi. Noah, Natalia, Emily, is your audio working all right?
Yep.
Can you all hear us?
Yes.
And you can see the screens all right?
I can see your screen.
All right. Let me go ahead and put this into slideshow mode, and I will mute myself.
All right, so hello everyone. Our project is identifying and examining sea breeze characteristics in the Houston, Texas region. My name is Emily Melvin. I am a third year from Georgia Tech, and I worked alongside fellow interns Eamon, Noah, and Natalia with the help of our mentors Mike Jensen, Dia Wang, and Sid Gupta from the Department of Environmental and Climate Sciences at the Brookhaven National Lab. Next slide, please. So our motivation is to improve our understanding of the factors that drive the life cycle of convective clouds. These clouds play an important role in atmospheric circulation, weather, and climate modeling. In the Houston region, sea breeze circulation is a driver of convective cloud formation. It is an excellent location for studying these effects because of the well-defined shoreline and consistent weather patterns. Houston is also under the domain of the Tracking Aerosol Convection Interaction Experiment through ARM. We use data from mostly the LaPorte site, which is shown on the map with the green marker. Next slide, please. So what is a sea breeze? A sea breeze is a flow of air from a body of water towards land, in our case from the Gulf of Mexico towards Houston. In the image on the left, you can see the general motion of the sea breeze and where convection will form along the front. It's caused by a difference in temperature between the air over land and the air over ocean. The air over land heats up faster during the day than the air over the ocean, causing it to have a lower pressure. And in the NextRad animation, you can see that front in the light blue moving across the area, and the LaPorte site is the yellow marker. Because there needs to be a large temperature difference between the land and the ocean, sea breezes most commonly are occurring in the early afternoon. Next slide, please. So to identify these sea breeze events, we looked first at radar data from NextRad, as you saw on the previous slide, and satellite data from the GOES-16 satellite. So you can see on the left the formation of some cumulus clouds along that sea breeze front as they move inward. And then to find the specific time of the sea breeze, we used ARM's surface meteorological data from the LaPorte site to identify a shift in wind direction to someplace between 100 and 200 degrees, which indicates a flow from the southeast. And we can confirm this by also looking for an increase in wind speed. And on this particular day, that happens around 18 UTC, which is around 1 p.m. in local time. So next slide, please. So the large-scale dynamics play a large role in setting the scene for sea breeze formation. As I mentioned before, there needs to be a large difference between the air temperature over land, which in this left plot, you can see is a dark red color, which indicates a lot hotter of a temperature, as opposed to over the ocean where it's a lighter orange. Also on the right-hand plot, you can see the vertical velocity, and the blue is indicating downward velocity and red is indicating upwards. And this needs to be fairly stable in terms of there not being any other large convective systems in the area. So in this case, there's a lot of yellow and light green. So that shows that there is relative stability, so it would be easy to form a sea breeze. And I'll pass it off to Noah.
All right, hello everybody. I'm Noah Smith. I'm a rising sophomore at Occidental College. So this plot that you see here is a composite of some ARM surface meteorological data from the LaPorte site. You can see on the x-axis we're taking the 2 hours before and the 2 hours after the sea breeze. and with the dashed line down the middle indicating the sea breeze itself. So in the top plot here, we're looking at residual temperature, which is the temperature when you subtract the mean temperature from that day. And you can see that temperature decreases right around the sea breeze start, and then starts to stabilize and even increase a little bit more due to the diurnal cycle after the sea breeze passes. You can see in the next plot, we have the relative humidity, which sees an increase around the sea breeze. We also see in the next plot an increase in the wind speed. And the last thing is on the bottom plot, this is the U component or the east-west component of the wind. And you can see that some of the westerly components before the sea breeze shift to be more easterly after the sea breeze. We also saw an increase in the magnitude of winds coming from the south, but since the winds were coming from the south before and after the sea breeze, it was harder to see that shift, so we left that plot out. Next slide, please. So kind of following along from that, we also looked at some wind profiler data, and this also helps us kind of look at the depth of the sea breeze front a little bit. So the left plot here shows the 0 to 1 kilometer height range, and the right plot shows the 1 to 2 kilometer height range. And the x-axis for both of these is the time in UTC, with the y-axis showing the percent composition of the wind directions. So because of the way that the coast is oriented near Houston, we're looking mostly for southeast and south winds, which are in these greenish colors. And you can see that around the afternoon sea breeze hours in the 0 to 1 kilometer range, we see a big increase in those values. You also see a little bit of an increase in the 1 to 2 kilometer range, but it's much less pronounced. Next slide, please. So this is looking at some Aero 5 models, and this shows the wind vectors and some divergence and convergence. So you see the top plot is showing before the sea breeze starts, and the bottom plot shows during the sea breeze. And you can see before the sea breeze, we're getting some more of these smaller wind vectors that are pointing more parallel to the coast and in the easter going east. And you see that as the sea breeze comes along, those wind vectors strengthen and start to go more in an onshore flow kind of direction. The red here indicates divergence, which is how much the wind is kind of being pulled apart. So it forms when faster winds are accelerating away from slower moving winds, and you see that really strengthen along the coast over the ocean in the sea breeze plot on the bottom. You also see some convergence in blue, which is when the wind bunches up as the faster sea breeze winds kind of hit the more stagnant land air. And this is what actually causes the convection associated with sea breeze and upward motion. Next plot. So here, kind of going off of that, we have the vertical velocity plotted. And so these plots show the vertical motion of the air. On the x-axis, we once again get the 2 hours before and after the sea breeze, with the line down the middle indicating the sea breeze itself. You can see on the top plot, we have the median radial velocity plotted, and the red colors, more positive values, indicate upwards motion or updrafts, and the blue or negative values indicate downwards motion or downdrafts. And we see a very strong concentration of updrafts right around that sea breeze front, which is comes from that convergence that we saw earlier. The bottom plot here shows the number of days that we have updrafts with greater than 1 meter per second velocities. And you can see the darker green colors indicate you have more days, and the lighter colors indicate less days. And once again, you see that big increase around the sea breeze start. And I forgot to mention the y-axis here is just the height. Next slide. So I'll be passing it off to Amon now.
Hi, everyone. My name is Amon Abdullah Smoot. I am a recent graduate of Texas Southern University, and I looked at sounding data. As you can see in this photo on the left from Scott, soundings are weather balloons that are launched at different times throughout the day that measure different atmospheric properties at different heights in the atmosphere. The main ones that I focused on are shown on this QT plot right here on the right. The dew point temperature, which is this green line, the air temperature, which is this red line, the wind bars on the side, which show the wind speed and the direction, the shaded red area, which is the convective available potential energy, or CAPE, which once again is the energy there is for convection in storms to form. The bottom area has the light blue shaded convective inhibition, or SIN, which is the thing that prevents convective clouds and storms from forming. And also you see the surface parcel temperature, which is the black line, which we use to calculate the CAPE and SIN. My work looked at the sounding days whenever there was a sea breeze front, on certain days where there was a sea breeze front, and we compared some measurements. So the first thing we looked at were the average temperature measurements, and we compared the pre-front data, which is in red on these plots, to the post-front data, which is in blue on these plots. You can see on the left plot that the air temperature increases after the sea breeze front, and it's similar with the dew point temperature on the right-hand plot, although it's only a slight increase. This was unexpected because sea breeze bring a decrease in temperature, but due to the diurnal cycle, the daily cycle, and an increase in temperature that follows that, and depending on the time the sounding were launched, this is why we are likely seeing this increase in these temperatures. The next thing I looked at were the wind measurements. On these two plots, the dotted line shows the change in direction. So first looking at this left plot showing the U wind, or the east and west component, we see that the wind changes direction after the sea breeze front. Before the sea breeze front, it is coming from the west, but after the sea breeze front, it is coming from the east. And on this V wind plot on the right, the wind direction does not change. They continue to come from the south. However, there is an increase in the wind speed, and this is confirming the ARM data that Noah was talking about earlier in the presentation. And then the last thing we looked at, or I looked at, were CAPE and SIN. Looking at this CAPE, we see that it increases after the post front, and we assume that this is likely due to the increase in temperature that our soundings are picking up. And we see at the SIN that it also increases after the post front, and this is likely due to some combination of the diurnal cycle and the sea breeze. So what this means is, while there is more energy for convection and storms to form, there is more that is preventing that from happening. And I will hand it off to Natalia to speak on her work.
Hello, my name is Natalia. I am a rising senior in high school, and I have been analyzing the radiation data. So the right-hand picture shows the SkyRad radiometer, which measures the downwelling solar radiation that is plotted on the right. The radiometer detects shortwave radiation, meaning solar radiation with wavelengths in the visible light spectrum. The blue line on the plot is the direct radiation or unscattered sunlight detected by the radiometer. The orange line is the diffuse downwelling radiation, meaning scattered radiation that reaches the surface, and the green line is the total downwelling radiation, which is all the radiation that reaches the surface and is detected by the radiometer. The earlier portion of the graph, from about 1 to 11 UTC, has very low values, as those values are during the nighttime in Houston as per the diurnal cycle, so there is minimal shortwave radiation then. The values increase throughout the day with a sharp decline around 17 UTC, as distinguished by the box, which aligns with our analyzation of sea breeze times usually occurring around that time. The graph then decreases again as the nighttime comes. The diffuse radiation, which is the orange line, increases around the sea breeze time, which would indicate there is more scattered radiation, meaning the radiation is being scattered by the clouds. Next slide, please. The image on the left side shows the total sky imager, or the TSI. This measures the quantity of radiant energy, or total intensity of radiation. The solid blue line shows the mean values recorded on sea breeze days, and the shaded area is the standard deviation. Just like the previous plot, there are minimal values in the beginning portion of the graph, as that is due to the diurnal cycle, and again is the nighttime in Houston. The values increase around 15 UTC, which is before the sea breeze, which would indicate an increase in cloud coverage. The values then decrease post sea breeze, meaning the sky clears up after the sea breeze. Next slide, please. In conclusion, our findings were that there was a quick decrease in temperature, followed by stabilization and then a slight increase. This is largely due to the diurnal cycle. We found that there was an increase in both humidity and wind speeds, as well as a shift in wind direction towards onshore flow within the 0 to 1 kilometer layer. This also is linked to strong updrafts around the sea breeze front. An increase in CAPE and SIN was detected after the sea breeze front. Lastly, the sea breeze also causes a decrease in direct radiation and total solar radiation, as well as an increase in diffuse radiation associated with cloud cover. It is important to note this is an ongoing project and future data may be collected and analyzed. Next slide. This concludes our presentation. Thank you for the opportunity to present here today.
Great, thanks everyone. That's a lot of great work there. Do we have any questions? We probably have time for one or two here. All right, Scott. Scott, are you there?
Yeah, I am. Sorry, I hit the wrong button on my iPad. This long into the pandemic, you might have. Hey, first of all, wow, that is incredible work. I absolutely love it. I got a kind of weirdly specific question because it always annoys me. What tools were you using for the satellite imagery you're showing there? It was like right up at the very beginning. I'm still yet to find something I'm really happy with. And how? Next slide. Next slide. You showed the animation there. Yeah, that's really, really nice. How are you getting the data and what tools were you using to plot it on the map?
I can answer this because I made that map. So I got the data from Goes to Go in Python. We use Python for all of our stuff.
Right.
So I used Goes to Go to get that, and then I just I plotted it using Python. I made them as like separate frames and then combined all the images together. So I just did it. Yeah.
Working with the projections with that gave me nightmares. So I'd love to. I'll touch base with Mike and others, but I'd love to see how you did it.
Yeah, sure. I can make sure I get that.
Thanks, Scott. Ernie.
Yeah, just a quick question. Very nice presentation. A lot of great work there. What was the magnitude of variability in the time of the sea breeze from day to day, and how often did you get a sea breeze every day? And maybe you mentioned that and I missed it there, but what kind of day-to-day variability in occurrence and in timing was there on that?
I can take this one. We didn't find it, first of all, every day. We found throughout June and the early parts of July, we found about 23 days that had CVs that were noticeable. And the timing also was not super consistent. It ranged anywhere from about 16 UTC to as late as 22 UTC.
Oh, wow. Okay.
Pretty big
Great.
change there.
Thank you.
Yeah, Bernie, there are definitely more days that we see sea breeze, but no, there are definitely more sea breeze days, but we don't see that usually from radar images because because of the background wind directions, there has to be a convergence there to be able to see on the radar images.
Okay. Great, thank you.
Scott, did you have another question or?
My bad, it's a residual.
Okay, no worries. Thanks everyone. We can move on to the next presentation here.
Did Sally just raise?
Oh,
Sally.
Yeah.
Yeah, I just had a quick question. I was wondering if any of you had thought about how you could apply that to look at the model data and see if the models are predicting the sea breeze well.
I don't think we've really looked at that much yet, but that is a good idea, something to think about for future work.
Right. Thanks, everyone. Next up, we have Mary with examination of SP2 signals for particle shrinkage. So Mary, please take it away here.
Great, thanks, Adam. All right. All right, looks good for all you guys?
Yep, looks good.
Excellent. All right, so hello everyone. My name is Mary Fucci. I am a SULI intern collaborating with the Environmental and Climate Sciences Department at Brookhaven National Laboratory, and my research focuses on the examination of SP2 signals for particle shrinkage. All right, so let me begin by introducing aerosols. So aerosols are tiny particles that are suspended in the atmosphere, and they come from many sources, both natural and man-made. So all particles scatter light and some absorb light, leading to either a cooling effect or a heating effect. A cooling effect when particles scatter light and heating when it's absorbed. Both of these have an impact on the atmosphere, and they contribute to climate change. There's many different kinds of aerosols. Depicted here are 3 that are of interest in atmospheric science. So polystyrene latex, or PSL, is a substance that we call a pure scatterer because it only scatters light and it doesn't absorb it. We're going to use green to denote anything that's a pure scatterer. So black carbon is a common aerosol that absorbs strongly throughout the ultraviolet, visible, and near infrared spectrum, making it black in color. You can think of soot. Brown carbon is a third aerosol of interest because it absorbs light preferentially at shorter wavelengths, such as ultraviolet and visible light. It absorbs blue and green light, so that kind of mixes and makes it a brown in color. So the single particle soot photometer, or the SP2, is an instrument that can measure aerosols individually. So they're individual particles. It's this little box here, and it operates by sending individual particles through a laser beam. And as the particles pass through the laser, it's either going to scatter light or it's going to absorb it and then incandesce. So when a particle is absorbing light, it's heating up. And if it heats up enough, then it's going to begin to glow. And this is what incandescence is. You can think of a metal coil on an electric oven and how it glows brighter and hotter the hotter it gets, and that's incandescing. So how much a particle scatters or incandesces in the SP2 is characterized by their scattering and incandescent signals. These signals tell us about a particle's mass and the coating. The SP2 is really well known for its use in measuring black carbon particles. However, as I showed you on the previous slide, black carbon isn't the only aerosol out there. So we're interested in the scattering signals produced from brown carbon, and we want to see if there's something unique about brown carbon that the SP2 can tell us. So this is kind of how it works. When a pure scatterer passes through the laser beam in the SP2, its scattering signals are measured. So these signals produce nearly uniform Gaussian curves. This is because the SP2 laser is a Gaussian beam. So the peaks are where we expect the center of the laser to be, because at the center of the laser, the most light is being concentrated on the particle, and therefore the particle is scattering the most light. However, when a brown carbon particle passes through the laser beam in the SP2, the scattering signals measured have this different behavior. These signals appear to begin Gaussian, but then slope off quickly with time. An explanation for this is particle shrinkage. As brown carbon travels through the laser, the particle is going to scatter and absorb the light. As the particle absorbs the light, it's going to heat up, and then it's going to evaporate and get smaller. So here's a plot of some real data of a PSL, or polystyrene latex particle, passing through the SP2 laser. You can see how its scattering signal is nearly a uniform Gaussian curve, just as I depicted earlier, and it's illustrating SP2's Gaussian laser beam. Now added to this plot is a scattering signal from a nigrosin particle in the SP2. So nigrosin is a black dye that is a brown carbon. It's the particle used in the SP2 for brown carbon research. So you can really see here by the brown trace in the plot how the nigrosin particle shrinks with time. It's an asymmetrical curve. So its diameter is getting smaller as the particle is being evaporated while it travels through the laser. Because the PSL particle scatters light and it keeps its shape over time, we can infer that the peak of its Gaussian curve occurs at the midpoint of the laser. So that value here is at 44. The nigrosin particle's peak happens much earlier than 44. So the difference between the peak of the scattering signal of our pure scatter, which occurs at the midpoint of the laser, and the peak of the scattering signal of our nigrosin particle characterizes the amount of evaporation. And we're going to define this quantity as x offset, since it's the horizontal offset between these two peaks. So we hypothesize that this x offset value will be positively correlated with the laser power of the SP2. So does increasing the laser power increase the value of x offset? Well, if the laser power is increasing, then more light is hitting the particle sooner, right? That would give us our peak scattering signal early, but then also cause the particle to shrink as some of the particle evaporates off quicker. So these are the kinds of questions that we're asking. And we want to use the sp2 in a way that hasn't been exploited yet by investigating brown carbon with it, as opposed to black carbon. So we want to better characterize brown carbon's behavior since it exhibits this particle shrinkage effect as it passes through the laser. So to investigate this, we analyzed nigrosin's x-offset at different laser powers. We chose 4 different laser powers and then collected the data of nigrosin scattering signals for each and identified the x-offset values. So, and here are the results of that data as histograms of the x-offset values for the nigrosin scattering signals at different injection currents. So just remember that injection current is what actually drives the laser power. So as the injection current increases, so does the laser power. So from these histograms, we're able to see that the average x-offset value increases as the laser power increases. So these results are what we expected, and they support our hypothesis. As the laser power increases, the peak offset between the scattering signal and the midpoint of the laser gets larger. So the mean x-offset value doubles from 2.7 to 5.4, and that's just with the 35% increase of laser power. So this means that the nigrosin particle is experiencing particle shrinkage as it travels through the sp2, and the extent of the particle shrinkage is related to the laser power. So from the examination of these sp2 scattering signals, we were able to define a quantitative relationship between particle shrinkage and the sp2 laser power. And to further future research, this method can be applied to ambient aerosol particles to detect particles that absorb in the near infrared but don't incandesce. So knowing how multiple types of aerosols, including brown carbon, interact with light helps environmental and climate sciences understand its role in the atmosphere. So with all that, I would like to thank Ernie Lewis and Art Sedlacek, as well as DOE, WDTS, SULI, and BNL, and thank you all.
Right, great work, Mary. Thank you. Are there any questions here? Yes, I'll ask quickly. It seems like this was a lot of, oh, Sally, go ahead.
Yeah, sorry, I can't get my hand raised. I have trouble with Teams, sorry. Yeah, this was really interesting. I was wondering on the slide that showed the X offsets at the different power, can you talk about that one, what causes the distribution in the offsets? Is that like different particle sizes of the nigrosin or different amounts?
Yeah, so we took samples of over like 50,000 particles that flew through the laser beam in the sp2, so you naturally kind of get this variation. The nigrosin particles are aerosolized at the lab, so you can kind of get this variation of the size of it a little bit. It might collect a small coating on it as it goes through, but this is kind of the main distribution of over like 50,000 particles going through it.
Great, thanks.
And that actually answers some of my questions here. It does seem like this was a lot of lab work. So what was the most interesting and the most challenging part of doing this?
Good question. So I didn't do the experiment part. I just been analyzing the data, of course, as like a remote intern. So to analyze a lot of this data, I had to learn a new software called Igor. And that was definitely the most challenging part for me. It's always learning a new language in 10 weeks and then having to present good data about it. So I would say that was the most challenging part. And then, of course, having to come in and understand the research that you're doing if you don't necessarily, or if you're not necessarily concentrated in the field at all.
I've been trying to push Ernie towards Python, but I don't know if that's going to happen.
I love Python. I swear by Python.
Look, I tell all the young ones, if I were their age, Python's the way to go, but you can't teach an old dog new tricks, right? So.
All right. Any other questions? All right. Thanks, Mary.
All right. Thank you all.
All right, we have our last presenter here, Kate, who is not actually a SULI, but is a grad student working with Allison on a GEM scholarship. So, Kate, please take it away here.
Let me go ahead and share my email, share my screen here. I hope everyone can hear me and see my presentation. So my name is Kate Johnson. I am a GEM intern at Brookhaven National Laboratory. I am also a PhD student at Carnegie Mellon University. And today I'm going to be talking to you about the impacts that Western wildfire smoke can have all the way on the East Coast. So to start, I want to talk a little bit about how wildfire smoke impacts climate change. Wildfires play a really important role in the forest ecosystems, right? They can be really helpful in clearing out old dead underbrush and promoting new forest growth. But wildfires have also been increasing in frequency in the last few years due to climate change. So it's estimated that wildfires could emit up to 20% of greenhouse gases globally. This would be mostly CO2. And as we know, greenhouse gases act as agents of climate change. So they trap the sun's radiation inside the atmosphere and cause increased temperatures. In addition, wildfires also emit black and brown carbon aerosols. And so these aerosols tend to have absorptive properties where they will absorb the sun's radiation and trap more heat inside the atmosphere, again, leading to increased global temperatures. It's estimated that up to 40% of atmospheric black carbon comes from wildfires. And so both the increase in greenhouse gases being emitted from wildfires and the black and brown carbon lead to increased global warming. This, as you might imagine, has the tendency to lead to a positive feedback loop where wildfires increase climate change increases wildfires. So climate change is increasing the frequency and the intensity of wildfire events. You can see this figure on the left is talking about wildfire frequency in the United States. And you can see there's some variability year to year, but there's a definite upwards trend in the frequency of wildfires we're seeing in the US. The figure on the right is talking about the amount of acres burned by wildfires in the United States. And you see the same trend, variability year by year, but a definite uptick since the 1980s up all the way to 2020, which is indicating that these wildfires are not only becoming more frequent, but much, much more intense, more acreage burned. This is not just a localized problem to the West Coast, where it seems that most of the wildfires occur. Wildfire smoke can, in fact, be transported all the way from the West Coast to the East Coast. So smoke plumes, because wildfires generate such intense energy levels, smoke plumes can be transported by continental scale winds from the West Coast to the East Coast. You can kind of see that on this map here. This is a wildfire smoke map. It's a smoke model. So you can kind of see a couple of hot spots in California, up in Oregon and Idaho. And you can see this plume of wildfire smoke just advecting all the way over to the East Coast. I've highlighted where Brookhaven is over on this map. So with increased fire intensities that we're seeing due to climate change, we have higher emissions. And because the fire intensity can propel the smoke up higher into the atmosphere, this will lead to smoke having a longer transport range. And so we would expect that we're going to continue to see large advecting plumes over the entire continent like this as climate change continues. This obviously will have impacts on climate and also on air quality. This could even impact things like solar power generation, whether or not enough incoming solar radiation is even able to get down to the solar panels during these events. So we wanted to look at the atmospheric impacts of these on the East Coast. And we wanted to start by looking at what the surface level impacts might be at Brookhaven. So we have a couple different instruments that can measure again, aerosol plumes on the surface. But I want to start by talking a little bit about brown carbon because we can use brown carbon as a wildfire smoke plume tracer. So as you might have heard in the last presentation, brown carbon are just composed of organic molecules. And because biomass burning is the primary source of atmospheric brown carbon, we can assume that any brown carbon particles that we're picking up in our instruments are probably from a biomass burn plume. So at Brookhaven, there was a time period in September of 2020 where there was a lot of Western wildfires. And we happen to have 3 different instruments running during that time. And these instruments measure aerosol absorption at different wavelengths. They're the PSAP and 2 types of ethylometers. And we know, as you also might have heard in the last presentation, that brown carbon is very highly absorbing in these near UV wavelengths. So this figure here, I've kind of shown the approximate absorption of brown carbon. You can see the absorption in this. Let me go back. This color bar down here is the visible light spectrum. And these purplish wavelengths are the near UV wavelengths. And so you can see brown carbon has very high absorption in these new near UV wavelengths. And it kind of drops off as the wavelength increases. So I want to maybe take a look at some of our in situ measurements. The top figure is the AE33, which is the ethylometer. Bottom figure is the PSAP. And the thing I want to point out most about this figure is that our instruments are picking up the same peaks generally. Their magnitudes might be different due to differences in the way each instrument takes their measurements. But generally, we are seeing the same peaks in both instruments, which is important. We also see a pretty significant spread here in the AE33. Note that the AE33 is the only instrument of the two I'm showing that has this near UV wavelength. We don't have that wavelength in the PSAP. And so we think that this increased absorption on the AE33 plot in the near UV wavelengths might indicate the presence of brown carbon. So we do indeed think that biomass plumes from Western wildfires did reach the surface of Brookhaven. So what we did to kind of confirm this theory is we calculated what the theoretical absorption in this 370 wavelength might be if the plume was only made of black carbon. We can do this with a relationship known as the Ångström exponent. I won't go too much into the math here. But this figure I'm showing here is the exact same figure we were just looking at, but with the 370 nanometer of the actual instrument and this theoretical 370 trace if the plume was only black carbon. This dotted line is what we would expect to see. But in fact, we're seeing absorption levels above this dotted line, which indicates to us that there is something else inside this plume, which is probably brown carbon. And because we know biomass burning is the primary source of brown carbon, we think we are seeing a biomass burn plume on the surface at Brookhaven. So we've looked at surface level data, but we were also curious as to what the total atmospheric column data might look like. So we use something called AeroNet, which is the Aerosol robotic network, and it's a collection of ground-based remote sensing instruments to give us this parameter called the aerosol optical depth, which is basically just a measure of the extinction of light from the top of the atmosphere all the way down to the surface. So to kind of give an example of this, if we had an aerosol optical depth of about 0.1, we might see this image of the Statue of Liberty. Very clear, you can see everywhere. However, if we had an aerosol optical depth of 1, we would probably see this much hazier image. It's a lot harder to make out everything in this picture. That's kind of just to give you an idea of the scale we're looking at with aerosol optical depth. So the first conclusion we made looking at the aerosol optical depth data was that high atmospheric column aerosols don't always match the plumes we see on the surface. So this top plot is again what we've been looking at, the absorption measurements that are taken at the surface. You can see there's a plume here, there's a large plume here. But these aerosol optical depth measurements, I want to point out first that they're very high. This is 1, and so they're reaching 1.2, 1.8. These are very, very hazy conditions on these days, but they don't necessarily match up with the surface level plumes that we're seeing. This indicates that a lot of the smoke might be sitting on top and not necessarily permeating down to the bottom layer. We can look at this also with a model. So NOAA has a smoke model. This is a lower resolution version of the HER model someone was showing us earlier. And what I want to point out here is that smoke models don't always capture surface plumes accurately, but they can be a good way to trace the overall plume advection across the continent. So again, I'm showing an absorption trace here, right? We can see the surface level aerosol plumes. I'm also showing the aerosol optical depth, which again, as I've mentioned, doesn't necessarily match up with the surface plumes. What I want to point out here, though, is in this figure on the right, we're looking at the total vertical column of smoke. So we can see on this date, 9/16, which is around when we have these really high aerosol optical depths, this indicates we have a lot of smoke over Brookhaven, and that is indeed what we are seeing in the model. The smoke levels are very, very high. However, on this same date, we see basically nothing on the surface, and that's not exactly true according to our surface instruments. So to kind of conclude, Western wildfire smoke can have both ground level and atmospheric impacts all the way onto the East Coast. And we know this because of the increased absorption that brown carbon has in the near UV wavelengths that we can use as plume tracers. We also know that the surface plume measurements are not always indicative of the total atmospheric smoke. As we just looked at with the AeroNet data, sometimes it seems that there can be a plume of smoke aloft in the atmosphere that doesn't quite reach down to the surface. And the third point I want to make is that smoke models can be very useful in determining the infection of smoke all the way across the continent, but the ground level predictions are not always what we're measuring quite at the surface. So a couple of future work bullet points that might be for this project would be to quantify the incoming solar radiation that's reaching the surface. There's a solar farm at BNL, and we could see how smoke plumes are impacting solar power generation. We could also do further smoke model validation using the in-situ surface level data to improve the models. With that, I want to thank my mentors, Dr. Allison McComiskey and Art Sedlacek, and Brookhaven, the National GEM Consortium, and the U.S. Department of Energy. And with that, I can take any questions.
Great, thank you very much. That was great work. It does look like we have a few questions here, so I'll go in the order they came in here. So Amy.
Hi, yeah, great talk. I work a lot with biomass burning aerosols, and maybe I missed this in the beginning. Do you know how long it took for the smoke to transport across the country? Or like, do you have an estimated time that, say, from emission to Brookhaven, it took, I don't know, 7 days, 3 days, 2 days?
That's a good question. We're estimating maybe about 4 days. There's actually some back trajectory modeling you can do to kind of try and confirm that, but the back trajectory modeling becomes more difficult to actually pinpoint the exact source. So we're not exactly sure, but around that range.
Okay, cool. I was just wondering because in my research, we found that brown carbon that's lifetime usually is, I don't know, less than 2 days. So we're about a week out in my research, and we hardly see any brown carbon. So if you guys see it, that's really interesting, but that's definitely something to kind of keep in mind, I guess, is the lifetime of the aerosol, that maybe like BNL picked up stuff from somewhere else that's a little closer.
Yeah, definitely. And I think this also might have to do with some of the secondary aging processes that might be happening to the particles in the atmosphere.
Mm-hmm. Yeah, but super cool. I never really thought that you'd see Western wildfire smoke on the East Coast.
Yeah, definitely.
Right. Next up, Jeff.
Yeah, I was wondering, did you say you're using some AeroNet data? Is that what you said?
Yes.
From the sun photometers? Because those are, some of those at least, are co-located with MPLNet, which is a micropulse LiDAR network. And from that, you could actually get the altitude of the smoke plumes, figure out where they are. They're this thick, and they do look like they're really thick, then you should be able to bounce a signal off them and find them.
Yeah, that would be a good idea to add to the future work. I haven't looked into any of that yet, but I'm sure I could find it.
Yeah, I think Judd Welton at NASA runs that. That's got it. Cool stuff. This brings me back to the days when I worked at the University of Maryland, and we were working with Maryland Department of the Environment. And some of these fires make a big deal. fairly long distance transport, we had an air quality violation from fires in central Quebec, which is, you know, basically there's nobody up there. And I remember that day because I was walking around campus and thinking, I smell wood smoke. And sort of drifting in and out of my personal threshold of detection. So I wandered into my lab and said, I wonder what the ozone is like. And it was astronomical. So all that aged smoke had a lot of extra stuff carried with it. So nice stuff.
All right. Thanks, Jeff. Scott.
Jeff kind of took a little bit of my thunder there because I was actually going to say, as well as the micropulse LiDAR network, and I need to use Adam's help a little bit for this as well. EPA has a network of ceilometers that we've been very much looking at trying to use in Chicago. What was the name of that network, Adam?
You're going to call me on the spot here. So it's actually, the EPA does have some ceilometers, but it's not an EPA network.
Yeah.
I want to say it's UCN. It's the Unified Ceilometer Network.
Yeah. Yeah. And now it's a tricky data set to get your hands on, but you can at least screen grab them. They have a bunch of quick looks that there. And exactly as Jeff said, they can help look. You can look at the height in the atmosphere. And if you actually look at the HER smoke model, they actually show you some information about the height in the model. So if you could correlate the height of the smoke layer in HER and the height of the signal in the LiDAR, then you can more definitively say whether it's probably smoke or not as well. That, and look if it goes over SGP or over any other sites we have on the way to New York as well. But very, very nice work.
Yeah, we'll have to look into that. I appreciate that.
Ernie.
Just a comment for the discussion. I seem to recall, and again, my aging memory, it might not be true, that when there was a smoke last summer, it was very hazy, but it was also very cloudy and stratus deck and so forth. So I'm not sure your ceilometers or your LiDAR even is going to distinguish between the two. I mean, it possibly will, but it wasn't nice clear sky options where you could just go, oh, the smoke's at this elevation. So just a comment on that.
Yeah, if you are Judd Welton yourself, you might be able to tease it out of a really nice fancy LiDAR, but chances are with a regular micropulse LiDAR, it just bounces off of whatever flies over, be it a bird or be it Ernie throwing mud over the fence. Either way.
All right, great. Any other questions here? I'm assuming the hand's still up our residual, so if not, thank you to all of our presenters here. This has been great, and really a big thank you to Ernie. He's the one that really gets us going because we all lose track of time, and Ernie's the one kind of hurting us. So definitely appreciate it, Ernie.
I was going to say thank you to Adam, who did all the logistics and planning for all this. All the speakers, this is really great stuff. Very interesting. The talks are, I think, higher quality every year we do this. And thanks to Shima and Sally and Jeff for taking time to attend and so forth also. So thanks all around.
Hopefully
I've been doing nothing but processing declinations of people who didn't win their grants for the last 2.5 weeks.
Oh, so ouch.
Welcome break from that, believe me.
I bet.
All right. Well, if there's nothing else, thanks again, everyone. We appreciate it. Hopefully we'll see many of our students here in coming years or as future DOE researchers. So
Always welcome back.
Yes. Thank you,
Future
everyone.
program managers. Just yeah, get here soon.
Thanks, everyone.
Thank you
all. Those were great.
Thank you, guys.
Bye, guys. Thanks.